Now, let's look at another example where recurrence relations appear naturally. So this is the classical Fibonacci rabbit population problem. And maybe you've heard of it, and it goes something like this. So you have a young pair of rabbits, so one male and one female, which is placed on an island. And rabbits do not breed until they are 2 months old. After reaching this age, each pair produces one near pair of rabbits each month, one male and one female, and let's assume that no rabbits die. And so the question is, or what we want, is to find the recurrence relation to count the number of rabbit pairs after n months. So in month 1, so when n is equal to 1, so so let's say for n equal to 1, you start with one rabbit pair. When n is equal to 2, the rabbit pair now is 1 month old, so they still do not have children. So you still have one, one pair. But now in month 3, you have 2 pairs, because you have the original pair that you had plus the pair that is old from before, right? In month 4, you have the new pair. So let's break it down like this. So this one is 1 new, here it's 1 old, here it's 1 old plus 1 new, and now the old one has a new pair. The new one just becomes old, so in total you now have 3 pairs, which is 2 old, because now you have the original old here, and the new one became old, but now also you have a new pair. And so on. You can continue to do this, and the question is, what does this sequence look like? So this is called the Fibonacci numbers. And so what do they look like, right? So if we let Fn be the number of rabbit pairs after n months, like we did, let's see how we can find Fn. So at month n, every rabbit pair from month n minus 1 is still alive. And so because no rabbits die, right? So we already have Fn minus 1, right? Pairs coming from the previous month. Now, there is also new rabbits born during months n. Now we ask, which rabbit pairs are old enough to produce these newborn pairs? Since rabbits do not breed until they are 2 months old, the pairs that produce the new rabbits at month n are exactly the pairs that existed at month n minus 2. So the number of newborn pairs is Fn minus 2. And so putting these two contributions together, we get that Fn is equal to Fn minus 1 plus Fn minus 2. And we have the initial conditions we saw from the beginning is just F1 equal to 1, F2 equal to 1, right? And so with this, you can compute any Fn recursively. So if you want F100, it's going to be F99 plus F98. And then to find F99, you do 98 plus 97 and so on, all the way back to F1 and F2. And in principle, you can compute this. And of course, we would like to know, and we'll see this, whether we can have a closed formula, right? Whether there's like a simpler formula than having to go recursively over all of them. Now, this is an important class of recurrence functions, and so it's an example of a linear homogeneous recurrence with constant coefficients. And so let's see exactly what that is. So a recurrence relation of the form, so you have a recurrence of the form an, and you can write an here, think of it as a combination of an minus 1 plus an minus 2 plus up to an minus k, where all of these previous an's are multiplied by some constants, right? So whenever you can write a recurrence in this form with constant coefficients, this is called the linear homogeneous recurrence relation of degree k with constant coefficients. Now let's see each expression here. What does it mean? So the linear part means that these these past coefficients, an minus 1, an minus 2, and so on, they appear on their own. They don't appear multiplied. So as an example, if we had an equal to an minus 1 plus an minus 2 squared, this is not linear because of this squared over here, right? Now, what do we mean by homogeneous? We mean that this sum here does not have like an extra plus a constant or something. There's no constant term that is being added here. It just depends on a combination of the past, and there's no like constant term. An example of a non-homogeneous would be what we saw with the Tower of Hanoi example. So hn equal to 2, hn minus 1 plus 1. This plus 1 here makes it into not homogeneous. And finally, what we mean by constant coefficients is that these are constants, right? They don't depend on n. They don't change. These are numbers. So C1 might be 5, C2 might be 7, maybe CK is 0, so on. Okay. An example of one that doesn't have constant coefficients would be something like Bn equal to n Bn minus 1. So as n grows, how much you multiply here also grows. And so this is an example where these are not constant coefficients. And of course, the degree we mean by how far back you go. This is the degree, this n minus k here.